Before we continue our lecture, okay, I think like the TA told me that because some students drop this class, so the group member may change, okay, due to student dropping the class. So so the TA actually suggests that the deadline for the project 2 is to be extended for 1 more week. Okay, so so I told the TA to be okay. So just want you guys to be aware. Okay, the deadline for the project 2 is extended for 1 more week. Okay, but if your teammate, okay, happen to drop the course, okay, and you need assistance, okay, please, contact TA, okay, and I will have the TA will help you to connect to other students, okay, for that. So last time we talked about different techniques to help training a neural network, such as batch normalization as well as transfer learning, right? And we know transfer learning help us to train the neural network when you do not have a lot of labeled data, okay? There's another technique called unsupervised pre-training, okay, that you could use in case if you do not have a lot of labeled data, okay? So basically, okay, of course you should try to gather as much labeled data as possible, okay? But if you cannot do that, okay, one way to help you to train the model is this unsupervised pre-training. Okay, what is unsupervised pre-training? Okay, it's something like this. Okay, so because you do not have a lot of labeled data, so what you do is basically, okay, every step you try to only train one layer. Okay, so for example, in the first step, okay, you train one hidden layer. Okay, and after you finish training, okay, when you move on to the second step, okay, you will freeze the layer that you just trained and add another hidden layer on top of that, and you again use a limited amount of training data, okay, the labeled training data, to train only the new hidden layer, the hidden 2 here. So you keep doing that, okay, to build up a deep neural network that can help you to tackle like a more complicated problem, okay. So this is so I mean, at each each step, basically you will freeze the layers you obtained from the previous process, and you only train one new hidden layer because you do not have a lot of labeled data. Okay, so this concept is called unsupervised pre-training. I'm sorry, unsupervised pre-training. Okay, so eventually, when you have enough layers, of course, you are going to use a smaller learning rate and maybe unlock a couple of layers to fine-tune your model. Okay, so this is like you are about to finish the training. Okay, you do that. Okay, so this technique is actually quite famous, okay, because like you know, the Jeffrey Hinton actually I mean used this technique in 2006, okay, to train a deep neural network, which actually mark the revival of neural network, okay. So of course at that time, okay, this unsupervised pre-training, okay, was used. I mean the model they use is called restricted Boltzmann machine, okay. This is a special neural networks, okay. We are not going to talk about this restricted Boltzmann machine, okay. If you are interested, you can check out Appendix E for the detail of this model, okay. The reason we don't talk about this is because, okay, this model is pretty much obsolete, okay. Nowadays, nobody uses restricted Boltzmann machine. If you see a paper that uses restricted Boltzmann machine, most likely that paper is over 10 years old, okay? The reason we don't use this RBM is because, okay, this RBM, when you train this RBM model, okay, for every iteration, you need to wait for this model to be what we call stabilized, okay? So it takes a long time to train this model, okay? So this is like you know, why this model is, I mean, nobody uses it anymore because it's just too difficult to train it, okay? However, okay, back to 2006, of course there was you know, 15 years ago, okay? So at that time, okay, RBM was still used. So Jeffrey Hinton used this, okay, along with the unsupervised pre-training to you know, to get the job done, okay. But nowadays, okay, for this unsupervised pre-training, we can still do unsupervised pre-training, but we probably do not use RBM anymore, okay. What we can use is autoencoder or GAN, okay, this type of spatial generative model, okay. So if you use autoencoder, okay, actually you can start from, you know, either here or here directly, okay. It is much more powerful, okay, and but of course, I mean, in this chapter we still do not, we will not talk about autoencoder or GAN, of course. I mean, we won't talk about it until we finish the CNN and RNN. So it will be covered hopefully toward the end of this class, okay? And when I start talking about the autoencoder, I will come back to revisit this unsupervised pre-training, okay? So anyway, so this is the unsupervised pre-training is the second technique you could use, okay, when you do not have a lot of labeled data. There's a third technique you could use, okay, in case you do not have a lot of labeled data, which is called, you know, auxiliary task. Okay, pre-training on auxiliary task. Okay, what is this? Okay, it's kind of interesting. Okay, actually, this concept is probably, I mean, because it does not require like require me to cover any new material to talk about the concept about this. So hopefully, like you know, you can grasp the concept real quick. Okay, basically it's like this. Well, you don't have the labeled data to train your task. Let's call this task A, okay? But you could easily, if you could easily find a lot of data, that you could use to train for another task. We call that task B. And it happens that task A and the task B are sort of correlated. Okay? So what you do is you can train a model for task B first using a lot of data you gathered. Okay? And then, okay, once you have the model for task B, okay, remember, like, we can do the transfer learning, right? Okay, you can use the previous, the first few layers from the model in the task B to construct the model for task A, okay, and apply the transfer learning basically, okay. So this is like an interesting approach, okay, an interesting approach. So you may wonder, okay, is it very easy to find a task that first it has to be somehow related to task A. Second, you have to have a lot of data, okay, for this task B that is easily obtained, okay. Let me give you an example, okay, here, okay. For example, if you want to build a system, okay, to recognize faces, okay, for example, like the surveillance system, okay, for many companies, they now use like you can just they just like have a camera in the front door and use the you can if you are the company employee, basically they just use the camera to capture your face to recognize if to distinguish, okay, those people who are not the company employee, right? I mean, this is like kind of like this is like one big application of like face recognition actually, okay. So, but the issue for this to build this system is that, okay, obviously you need a model that recognizes the company employees, right? But okay, if you are in a company, okay, if the company tell you, okay, we need to build a face recognition system, and the company asks you to submit your photos. How many photos can you submit to your company? Okay, maybe 10, 20, that's a lot already, right? Okay, I mean, it's impossible for a company to ask the employee, each employee to submit like hundreds of photos. That's just outrageous, right? It's just not possible, right? I mean, if company can only gather like maybe a couple of photos from each employee, how can the company build a face recognition system, okay, to recognize company employee, right? So that's the issue, right? This is obviously the issue about lacking labeled data set, right? We don't have a lot of labeled data set, okay, when the company decide to build a face recognition system. But we do know that, okay, a lot of people have like an Instagram account, right? And on those Instagram account, okay, people put their photos there like a lot, right? Okay, although we know those photos may not be the company employee, but that's fine, okay? We can train a model, okay, that maybe be able to identify, let's say, okay, if two photos, okay, represent the same person based on their face, the face in the photo, basically. I mean, you can easily get a lot of such data set from the Instagram. Why? Because as long as these two photos comes from the same Instagram account, most likely the person in the photos are the same person, right? Right, will be the same person. So you can gather a lot of such data set to train a model to basically tell you, okay, if the person in these two photos represent the same person or not. Okay, so now, okay, suppose you have this model. Okay, you can easily transform this model to become like the surveillance system, like face recognition system for the company. Basically, just gather your company employee photo and use that. Okay, and you get another photo from camera. Okay, the incoming visitor. You just compare this one with like the employee's photo and see if they match or not, right? So this is like one way, one of the pre-training on an auxiliary task, where that's very easy to be applied to solve this face recognition system issue. Okay, that the company wants to build. Okay. So another example, which is actually very very important. It actually the NLP like especially in recent years, the NLP research gets a big boost from this the pre-training on auxiliary task concept. Actually, we know like NLP, in order to train a model that recognizes some language features, it's difficult, right? It's difficult. But we could do something like this. Okay, for example, okay, we can get a lot of text from the World Wide Web. For example, Wikipedia. Okay, Wikipedia has a lot of sentences, right? You can use a crawler to easily download those sentences. Okay, and then okay, you can just randomly remove some words from the sentence. For example, like this sentence, what are you saying? You can randomly remove this word, okay, here. So this word can be either are or were, right? So you can use this way to train, because you have vast amount of data, right? Because you download the whole Wikipedia page, okay? So there are, millions of sentences, okay, that you have. And because this word removing is done by you, right? It's done by you. So you know the ground truth, right? You know the ground truth. So you can use this data set, okay, to train a model, okay? This model, obviously, the task is to fill the missing words, right? But because, okay, if this model performs well, then you can imagine this model should have a very good understanding of this language, right? Otherwise, it wouldn't be able to fill out those missing words, right? Okay, then you can utilize that model, okay, even though it's used for just like filling the missing word. But you can use that model, okay, for other NLP tasks. Because any NLP task, okay, the model is required to have a good understanding of the language, right? So basically, okay, this concept, okay, actually, help the progress of NLP research a lot. Okay, nowadays, nobody if you are doing any NLP research, nobody trained a model from scratch. There are so many pre-trained model, okay, out there for any NLP task. For example, okay, the most well-known model is called BERT, B-E-R-T. Okay, there are also other models such as because they are like a variation of BERT, so they are called like a raw BERT, L-BERT, you know, pretty much any word with BERT in there. Okay, so just want you to be aware. Okay, this pre-training on auxiliary task is very important. Okay, and so for this example, do you consider this as supervised or unsupervised learning? Remember, like okay, in machine learning, okay, supervised learning means we learn from labeled data set, right? Basically, you know the ground truth, and you train a model, okay, to match with the ground truth as much as possible. That's the basic idea of supervised learning. For unsupervised learning, on the other hand, you have the data, but you do not need to provide label. You just have the model to learn from the data without the label. That's called unsupervised learning. Okay, in general, unsupervised learning is more difficult than supervised learning, by the way, because obviously if you don't have a ground truth, it's more difficult to learn anything from the data. Okay, however, how about the one that I just mentioned? Okay, when you download these millions of sentences and you actually remove some words from these sentences intentionally, okay, to create a training data. We call this thing as self-supervised learning. Self-supervised learning, because we know, we sort of create the label data by ourselves. Okay, this ground truth is not, really done by manual labeling. It is done by a program that randomly remove the words from the sentences, right? So this is the label data are automatically generated. Okay, so we call this type of learning as self-supervised learning. And because for this self-supervised learning, you don't need to have to pay like much label work for to label the data. Okay, so we consider this self-supervised learning as one type of unsupervised learning. Okay, just want you to be aware. Okay, the type of learning. Okay, this thing present, but I'm not saying. Okay, I'm not saying pre-training on auxiliary task has to be, the task has to be self-unsupervised learning, self-supervised learning. It does not necessarily have to be. Okay, as long as you can sort of find another task which is related to the task you want to resolve, and it's much easier for you to gather a lot of data for that task. Then we call that, pre-training on auxiliary task. Okay, as for that, that task B is self-supervised learning or not. I mean, well, if it's self-supervised learning, of course it's easier. But if it's not, okay, if you are able to, label the data with a lot lower cost, with a much lower cost, well, you can do that too, right? So we have, if you do not have a lot of labeled data, okay, we talk about 3 different ways that help you to deal with the problem. The first one is transfer learning. The second one is pre-training on auxiliary task. The third one is unsupervised pre-training. Okay, unsupervised pre-training. So how about the speeding up the training? Okay, speeding up the training process. Okay, because training a large neural network, okay, it can be very slow. Okay, so previously we already talked about a couple of ways, to increase the training speed. For example, okay, we can apply a better initialization strategy, okay, such as Lechon, He initialization, Xavier initialization, remember? And we can use better activation function, such as variant of Riru, as well as ELU or Siru. Okay, those activation functions, also help you to train the model faster. Okay, another approach is use batch normalization. Okay, that's obviously like remember I told you using the batch normalization speed up the training by some studies say it speed up training by 17 times, right? Okay, and transfer learning, obviously, this reusing part of the pre-trained network. Okay, transfer learning, obviously, not only reduce the required amount of labeled data set, it also help you to get your model trained faster, obviously. Okay, but are there other techniques that we could use, okay, to speed up the training? Okay, one thing we could use is the optimizer. Okay, optimizer, the faster optimizer. So far, we only use one optimizer, right? The stochastic gradient, SGD, right? Stochastic gradient descent. Okay, and there are a lot of optimizers which are much faster than the regular gradient descent optimizer. Okay, so in here, okay, we are going to talk about a lot of optimizers, okay, today. Okay, so it is one of the important topics today, actually. Okay, such as momentum, Nesterov, okay, NAG basically, okay, ADA grade, RMS prob, and Adam Max and Naden. Okay, they are all like more advanced optimizers that can help you train your model faster, basically. Okay, so the first one is momentum. Okay, so what is momentum optimizer? Okay, remember like the rolling ball in on the surface example when I talk about like gradient descent. Remember that, right? Okay, so basically gradient descent pretty much represent like you're trying to find try to advance to the lower position, okay, in the cost function, right? Okay, so think about this, okay. If you have an uneven surface, okay, and you put a ball on the ground, okay, and the ball is going to roll toward the lower location, right? And actually it's going to, if